So the first thing I want to do is this example. And this example is going to be another example of a geometric series. We've written geometric series like this. I want to write the geometric series in a different way. This is another common way to write it. Instead of calling the common ratio x, I want to call it common ratio r, which is a natural thing to do since r is the first letter in ratio. You'll often see geometric series written like that. And I can write it with summation notation as well. What does it sum to as long as the absolute value of r, the common ratio, is less than 1? We know it sums to the first term, a, over 1 minus the common ratio. So that's going to be a over 1 minus r. What I'd like to do to start class off with today is start with a function and figure out a series for the function. Usually we've done the other way around. In fact, on Monday, we started with the function. We started with the series 1 plus x squared plus x cubed plus x to the fourth, etc. So a was 1 and r was x. And we saw, because of this, that it equals 1 over 1 minus x. And I made an animation with Mathematica showing you the convergence. I also did it for e to the x and sine of x and cosine of x. Let's do the reverse process. Let's start with the function. And here's the function I'm going to pick. F of x equals 3 over 4 plus 5x. And let's try to use this exact same formula to expand this function. That's the word people use, expand this function as an infinite series. To write it like that. However, it's not clear how to do that if I want to use this formula. Is a 3? And if that's the case, what is r? I mean, is it 5x? Is this 4 a problem? Because there's a 1 right there. And the answer is you do have to adjust for those things. The first way to try to make it fit this expression, to make it look like that, a over 1 minus r, is to make sure there's a 1 in the first spot. How? Well, factor out a 4. Because 4 equals 4 times 1. That puts a 1 there. Of course, if I do factor out a 4, I got to factor it out of both terms. So the second term is not a 5x, instead it's a 5x over 4. So at least I've got a 1 there now. It's a little closer to that. How else do I need to compensate? Well, this 4 still seems like maybe it's a problem. Now I could multiply the entire fraction just by 1/4 if I get rid of the 4. Or by doing that, I could also bring the 1/4 up into the top. 3 times 1/4 is 3/4. And that's what I'll do. And also, if I'm going to make it match this, I need a minus sign instead of a plus sign. It's a plus sign. Well, that's easy. Do a minus of a minus. And all of a sudden, by doing those algebraic tricks, I've now rewritten this function in the form a over 1 minus r. There's a, there's r. So, according to this formula, which is true, as long as the absolute value of r is less than 1, r itself is between -1 and 1, I can use it in the reverse, from right to left. I can expand this function as a series. A is 3/4. R is -5x over 4. A times r would be 3/4 times -5x over 4. A times r squared is going to be 3/4 times -5x over 4 quantity squared. A times r cubed is going to be 3/4 times -5x over 4 quantity cubed, etc. Don't forget your plus dot dot dots. If you forget the plus dot dot dots, it's wrong. It's only an approximation if you forget those. You've got to emphasize for full credit that it's an infinite series. It's the infinite series that gives you equality. though only for certain values of x. Only when negative 5x over 4 is less than 1 in absolute value. Let's simplify this. Three fourths times negative 5 fourths will be negative 15 sixteenths. Negative 5 fourths squared will be 25 sixteenths. Times 3 fourths will be 75 64ths. Don't forget the x squared. Right, I think we're doing so fine so far. Double check, make sure I don't make a mistake. Negative 5 fourths cubed, negative 5 cubes, negative 125. 4 cubed, 64. Negative 125 times 3 is minus 375. 4 cubed, 64 times another 4 is 256. Etc. Don't forget your plus dot dot dots. For what values of x is this true? This equality right there is true if the absolute value of r is less than 1. R is negative 5x over 4. It's a property of absolute values that the absolute value of a product, negative 5 fourths times x, say, is the absolute value of the first number times the absolute value of the second number. Of course, the absolute value of negative 5 fourths is positive 5 fourths. Then I can multiply both sides by 4/5 to say this converges when the absolute value of x is less than 4/5. Meaning x itself is between negative 4/5 and positive 4/5. That interval of values of x has a name. It's called the interval of convergence. Interval of convergence of the series. And also it's the interval where the series equals the original function, 3 over 4 plus 5x. The series has a special kind of name. In fact, it's got 3 special names. Most fundamentally, the series is called a power series. In either form, it's a power series because it's got powers of x. More generally, it might have powers of x minus something. And that will be the last example we do today. A power series because it's got powers in it. It also happens to be a geometric series. But there are some power series that are not geometric series. Got that? Terminology is super important in this stuff, right? You want to think about this stuff consistently while you're learning it, to get this terminology in your mind so you get what I'm talking about in class. If there's no other reason to try to work at memorizing to some degree, try to be motivated to say, I want to understand better what's going on in class. What is Dr. Kinney talking about? Power series in general is a series with powers of x, or we will see powers of x minus something. It's centered somewhere. It's about or at x equals something. When the power series has powers of x minus some number, that number you're subtracting is what it's a power series about. I'm not subtracting anything. I've got x's that are powers, x, but that's equivalent to x minus 0, 2 powers. So this power series is about x equals 0. because, for example, x squared is x minus 0 quantity squared. It also happens to have a couple other names that more refer to the fact that it's a power series representing a function that you started with. It's also called a Taylor series, and it's also called a Maclaurin series. What? How could it have two different names after two different people? Yeah, Taylor and Maclaurin were two different people who lived in the 1700s. Also known as Taylor series for f of x about x equals 0, or just more plainly, a Maclaurin series for f of x. Our book mostly just says Taylor series. Might have mentioned Maclaurin series once or twice, and I will mostly say Taylor series. Taylor series is the more broad name where it's about any number. Maclaurin series is specialized. It's a Taylor series where you're doing it about 0, x equals 0. Both guys from the 1700s have their name attached to this. Taylor series are power series, but we typically think of them as power series for a given function. And when we looked at the mathematic animation on Monday with e to the x and sine of x and cosine of x and the flapping of the wings, we were looking at Taylor series approximations, Maclaurin series approximations for those functions, e to the x, sine of x, cosine of x. And the approximations were getting better and better as the number of terms that I included got higher and higher. The interval of convergence is important to think about as well. In this case, the interval of convergence goes from -4/5 to +4/5, not including the endpoints because you have strict inequalities there. -4/5 to +4/5. Notice such an interval is centered at 0. The power series here is about 0. It's centered at 0. The interval of convergence is centered at 0. All the numbers in here is where the series converges. Now that's not a circle, but I am going to call this distance its radius. And it's called the radius of convergence. Radius of convergence, that distance right there, it's 4/5, 0.8. How can it be a radius if it's not a circle? Well, it's certainly the distance from the center of the interval to the endpoints, either endpoint. If I decided, and many people do decide to do this, I decided to allow myself to plug in complex numbers in for x, then this real axis would expand to what's called a complex plane. I would draw in what's called an imaginary axis going up and down, but I would draw it. It would be there. And this interval would become a circle. And it would truly be a radius of the circle. A disk would be the inside of the circle, actually, is the more official way to say it. Tracking with me? This is supposed to be kind of cool. More fun than using convergence tests. Having fun? I'm having fun. Before this class, by the way, I hardly ever did all the thumbs up, but I don't know, with you guys, I've just been doing lots of thumbs up. We're going to do another example at the end that with the same function, but we're going to expand it about a different value of x. We'll expand it about x equals 1 and get a different answer. But it still represents the same function, amazingly. Over a different interval of convergence, though. Let's check this with Mathematica. One way to check it is to write the series in summation form. So click your summation button. It's easiest if you think about it in the unsimplified form, to think about the pattern there. It's a geometric series. In fact, k goes from, say, 1 to infinity, though I could start k at 0 instead if I wanted to. First term is 3/4. Common ratio is -5x/4. First term has that thing to the 0th power, so I need a k minus 1 power, not a k power, if I start k at 1. Does this simplify to the original function? Yes, it does. Yay, that's one way to confirm the answer. Here's another way to confirm the answer when it might seem like the pattern of the series is not so clear. Series. Capital S at the start, plug in the function, put a comma. Probably want to write this down, by the way. Then put in curly braces the variable x, comma, then put what the series is about. 0, right? That's the center of the interval of convergence. The example at the end of class, we'll put a 1 there. Then put a comma, and then put the highest power of x to include in the answer, 3, so that we see that we match this simplified answer, hopefully. And we did in the last class, and I got the right answer. Yep. 3/4 minus 15/16x plus 75/64x squared minus 375/256x cubed plus what? What is that? Plus 0 times x to the 4th? That's not right. Mathematica, you goofed up. That's not a 0. It's big O. Anybody ever heard of big O notation? Okay, a few people nodding yes. Big O. What? Big O? What does big O stand for, and why is there an x to the 4th there? This is just shorthand, mathematical shorthand notation to say plus ... where all the other things after the ... are x to the 4th and higher powers. Big O is a topic in discrete math, most typically, related to efficiency of algorithms. But here you can effectively think of it as order, big O, the O standing for order x to the 4th and higher degree or higher order terms. Sometimes people abbreviate it HOT, hot, for higher order terms instead of plus ... These functions, if you truncate here, if it's just the finite series, this thing here, it doesn't equal the original function because I'm truncating. It's no plus ... there. They're not equal, but they are really close together when x is close to 0. And if I used even higher order terms, say I went out to the 20th power of x, and plotted that function, copy and paste, fun. Woo, just copied and pasted there. We are trying to approximate the blue graph. And that green graph is doing a really good job, better job than the goldish graph, including out to near x equals 4/5, which is 0.8. And negative 4/5 is, it's doing okay out there, which is negative 0.8. Doing pretty good. And if I included even higher to order terms, it would do even better. In the limit, as the number of terms goes to infinity, the partial sums approach the actual function when x is between negative 4/5 and positive 4/5. They're actually equal to each other. You do get equality in the infinite sum. Don't remember, as I've said, we're not literally adding up infinitely many things. We're only pretending to. But we are rigorously defining what we mean when we say we're pretending to. And it does turn out to be useful still. One thing it's useful for is the original function approximation to any degree that I want. I can truncate to any degree that I want. Now, for such a simple function, you might say, well, but what's the big deal? Why bother? But for more transcendental functions, non-algebraic, this is algebraic. Transcendental functions are non-algebraic functions, meaning like trig functions, sine, cosine, e to the x, natural log of x, arctangent. Those are called transcendental functions because they're not really an algebraic character. How do you program a calculator to compute those things? You got to use algebraic kinds of things that involve basic arithmetic, adding, subtracting, multiplying, and dividing. It's easy to program circuits to do that kind of thing, not so easy to program them to compute signs of things. And the infinite expansion is useful for other things as well. Last topic for today, last example. Let's go back to our original example and let's expand it about a different center for the interval of convergence. What I'm talking about here with these intervals of convergence and power series is section 9.5. You are going to have some problems from section 9.5. Let's expand about x equals 1 now instead of x equals 0. I'm still going to use the geometric series formula. A over 1 minus r equals a plus ar plus ar squared plus ar cubed plus dot, 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 if the absolute value of r is less than 1. I'm still going to use that. But what I'd like the r's to be, to expand about x equals 1, is I'd like the r's to involve x minus 1 instead of x. Like the r to involve x minus 1. So it's even trickier, but it can be done with this kind of example. First thing to do is to replace x with x minus 1. But you can't stop there because that would be cheating. That'd be wrong, I should say. By replacing x with x minus 1, I really subtracted 5 from the bottom of the fraction, so I have to compensate by adding 5. 4 plus 5 is 9. Now I'm in a similar situation as before. I want a 1 there instead of a 9. So factor out the 9 like this. I also, because of this, want a minus sign instead of a plus sign, minus negative 5/9 times x minus 1. I almost made a mistake there. I need to divide the negative 5 by 9 because I factored the 9 out of both terms. I'm almost to this form. Just bring the 9 up into the top of the fraction as, make it a 3/9 in the top, which is 1/3. Now I've done it. That's now in the form a over 1 minus r. So now use the geometric series formula to say this equals, first of all, a 1/3 plus a times r plus a times r squared use parentheses like I'm doing, plus a times r cubed plus dot, dot, dot. Simplify. 1/3 minus 5/27 times x minus 1 plus negative 5 squared is positive 25 over 9 squared is 81 times 3 is 243 x minus 1 squared. Then minus negative 5 cubed is negative 125, negative 125, 9 cubed, 729 times 3 is 2,187 plus dot, dot, dot. Looks like a completely different answer than the previous time we did it, and it is. But it's still equal to the original function. However, about a different interval. It's an interval centered at 1 instead of 0. The other example remember if this is your handout or the other class. It was the interval from -4/5 to +4/5. What's this one? The absolute value of R, here's R, must be less than 1. That's equivalent to 5/9 times the absolute value of x minus 1 being less than 1, which is equivalent to the absolute value of x minus 1 being less than 9/5, 1.8, which is equivalent to x itself being between -4/5 and +14/5. That's -0.8, and this is +2.8. The interval of convergence is centered on 1, has a radius of 1.8. It goes from -0.8 to +2.8, not including the endpoints. Sometimes in intervals of convergence, you do include the endpoints, and sometimes you do not. And sometimes you even include one endpoint, but not the other. With geometric series, you do not include the endpoints. That's the interval of convergence. That's the radius of convergence. And let's give me 30 seconds. We'll check the answer in Mathematica. Copy and paste this series code down here. And all we have to change to confirm the answer is change this. Well, let's change that back to a 3. Change the 0 to a 1 because we're doing it about 1. Do we have a match? Yes, it looks good. And again, that last term you see in Mathematica is big O of x minus 1 to the 4th. That means it's x minus 1 to the 4th plus and higher powers. Hot, higher order terms, they're called. Hot. Okay? HOT. Have a good day.